In simultaneous localization and mapping, there are many software and hardware parameters that need to be tuned. However, this tuning should also take into account the structure and motion of the camera. The set of all combinations of various system parameters are represented by a Pareto front of possible points, where each point on the front represents an optimum set of parameters given the desired performance metrics. In here, points A and B both are better than C. This example application has 4 design spaces: algorithm, compiler, hardware, and motion and structure, where the latter is a new concept introduced in this paper. Each space has a set of parameters chosen from a Pareto front, depending on the required performance metrics. The MS parameters are calculated using information theory. These parameters, together with images, are used to control the motion of the camera, such that the desired performance metrics are maintained. Given 2 consecutive intensity images, their divergence is calculated using the KL divergence of normalized intensity histograms. Similarly, the divergence of 2 consecutive depth images is calculated using KL divergence of spherical histograms. It is shown that high information divergence is equivalent to poor performance metric. Thus, to have a good performance, information divergence should be limited. As MS parameters, we determine the maximum intensity and depth divergence values experimentally, using datasets. We determine these values by skipping frames at regular interval and calculating the frame-to-frame divergence. To generate one point on the Pareto plane, we first generate a random sample of the algorithmic space parameters. We then specify a frame drop rate, and by running the algorithm with these parameters on the corresponding image sequence, the metrics are calculated, together with the corresponding MS parameters. This process continues, each time adding a Pareto point, until we have the Pareto front determined. The Pareto front is later used to specify design space parameters based on the trade-off between different performance metrics. We propose an active SLAM using the proposed parameter optimization. Our objective is to achieve the desired performance metrics by controlling the incoming information flow. In other words, we guide the camera such that the information divergence is not more than the permitted maximum information divergence. Here is the active SLAM guiding the camera on ARM. The video has been played 2 times faster.